Hello everyone, welcome back. In this video we're going to finish section 14.8 and therefore finish chapter 14. And this video is going to be a little shorter than the previous ones, and we're going to start it with an example. Another example of an optimization problem where we use Lagrange multipliers. So this problem says find the extrema of x squared plus 2y squared on the circle x squared plus y squared equals 1. So before we start, why don't we just take a look at this function itself and the constraint. So the function x squared plus 2y squared creates this elliptic parabola, it creates this surface, where you can see that it's wider in the x direction than it is in the y direction. So if I were to take cross sections or look at the level curves of this surface, they would be ellipses. We can look at it from the top, and we have an ellipse at the top. And I want to find the maximum and minimum values of this surface if I just look at the slice of the surface that's above the unit circle. And I guess I really don't have to show you the unit circle, but there it is. So that's what we're trying to find, just the slice of this surface above the unit circle. If we go back to the notes, we're going to use the method of Lagrange multipliers. Here I'm only dealing with functions of two variables, so my gradients are going to be vectors with only two components. I'm going to take the gradient of each equation. So one equation is x squared plus 2y squared, so I take a gradient, I get 2x for y. The other equation, my g equation, is x squared plus y squared, and so I take a gradient there, I get 2x 2y. And then I multiply the gradient of g by a Lagrange multiplier lambda. So I get the system of equations 2x equals lambda times 2x. Those are the x partial derivatives of both f and g. 4y equals lambda times 2y, the y partial derivatives of f and g. And then the constraint itself, x squared plus y squared equals 1. This is the system of equations I want to solve. And I'm going to start by looking at this first equation and saying, okay, what if I get all the terms on one side? I subtract 2x over, I can factor a 2x out, and then I get 2x times lambda minus 1 equals 0. Well, this leaves me with two possibilities. The first possibility is that x equals 0. The second possibility is lambda equals 1. And so I have to look at these two cases separately. In the first case, if x equals 0, then I can use this constraint to figure out what y has to be on the unit circle. If x equals 0, what does y have to be? Well, it's pretty easy to solve. Y has to be plus or minus 1. Notice in this case, I don't care about the value of lambda at all. You can go figure out what lambda has to be if x equals 0, but it doesn't matter. All we care about in the end are the x and y values. And so I get 2 points, 0, 1, and 0, negative 1, that I need to check. So that's what happens in the first case if I consider x equal to 0. In the second case, I consider what happens if lambda is equal to 1. If lambda is equal to 1, I go to the second equation and solve for y. So 4y equals 2y. That means y has to equal 0. It's the only possibility. So then, if y equals 0, I again go back to my unit circle, my constraint, and figure out what x has to be. And x has to be plus or minus 1. So that gives me 2 more points I have to check, 1, 0, and negative 1, 0. So now I have 4 points total on my circle that I need to plug in to this function, x squared plus 2y squared, and see what my maxima and minima are. So if I plug in 0, 1 or 0, negative 1, both of those give me a value of 2. If I plug in 1, 0 or negative 1, 0, both of those give me a value of 1. So the maximum value is 2. It occurs in 2 locations. The minimum value is 1. It also occurs in 2 locations. Let's go back to our graph and see what's happening here. So this curve that I'm showing here is just the slice of f that's above the unit circle. So if I look at this curve, I have 2 maxima. The value of the maxima is 2 if I look at the z-axis. The x-coordinate of both of these maxima is 0. And if I look at the y-coordinate, I have that the y-coordinates are negative 1 and positive 1. I also have 2 minima. Here they are. Their value is 1 if I look at the z-axis. Their y-coordinate is 0. And their x-coordinates are plus or minus 1. So that agrees with everything that we found on paper. Okay? So geometrically, we see the same thing. It's just maybe a little more intuitive if we look at the curve. Now, the next thing I want to show you is that curve on our surface itself. So here's the surface, x squared plus 2y squared again, and I've highlighted just the portion of this surface that is above the unit circle. So that's that same curve I showed you before, but now it's on the surface itself. So you can see how those maxima and minima are on the surface. If we look inside of the surface, if we look from above, we can see the unit circle. That's the piece that's just above the unit circle. And the last thing I have to show you, I have again the red unit circle. This is our constraint curve. And then these ellipses are level curves of f. So you can see that the location of our two minima, negative 1, 0, and 1, 0, the constraint curve shares a tangent with this level curve, which is where the f equals 1. And at the locations of our two maxima, 0, 1, and 0, negative 1, the constraint curve shares a tangent with this level curve, which is the curve where f equals 2. And so we have two maximum, and it's 2 minima, and the minima are 1. And so that shows you that this geometric interpretation of Lagrange multipliers, where you're going to find the maximum and minimum values, where your constraint shares a tangent with your level curves, you can see that clearly from this plot. Okay, going back to the notes, the two examples that we've done, one with a function of 2 variables, one a function of 3 variables, we've only had a single constraint. So is it possible to have multiple constraints? Sure, you can have multiple constraints. So what happens if we have two constraints? Let's say I want to maximize or minimize some function subject to one constraint, g equal to k1, and a second constraint, h equal to k2. Well, what changes is that our system of equations becomes larger. I add the second constraint as an equation, and I get another Lagrange multiplier. So now I'm saying that the gradient of the function I'm trying to maximize or minimize is equal to 1 Lagrange multiplier lambda times the gradient of g, plus another Lagrange multiplier mu times the gradient of h. So this is the Greek letter mu. And so now I have a system of 5 equations in 5 unknowns. I have it written out here. These are just the 3 equations making up that gradient equation above. Again, the gradient of f is equal to lambda times the gradient of g plus mu times the gradient of h. And then the two constraints, g equal to k1, h equal to k2. The 5 unknowns are x, y, and z, so the points that satisfy these 5 equations, and then lambda and mu, my 2 Lagrange multipliers. Really, the solutions I care about are the points x, y, z. I'm going to plug those into f and figure out what the largest and smallest values are, depending on what I'm looking for. I might also find lambda and mu while I'm working this out, but in the end, I don't care about the values of lambda and mu. I'm just using these to solve the system. Let's say you had a third constraint. If you had a third constraint, you would just add another Lagrange multiplier times the gradient of that constraint, which would give you here plus another Lagrange multiplier multiplied by partial derivatives of some other function, and then you would need to add the constraint itself as another equation. And you can do that as many times as you like, for as many times as many constraints as you have in the optimization problem you're trying to solve. All right, that's it. That's chapter 14. I think there's an example of one of these in the book. I'm not going to go through an example. Just wanted you to know that if you work in an area of optimization, you're doing some kind of optimization problems in some other class, or you end up working in an area that does optimization. For instance, a lot of machine learning, data analysis use optimization all the time. This is a method you can use to optimize functions. And you can have as many constraints as depends on your problem. You just keep adding Lagrange multipliers times gradients. All right, so that's going to be it for chapter 14. You have an exam coming up in a week, and then after that, we'll get into chapter 15, which involves double and triple integration.